In this section, we're going to learn how to look at structures of acids to be able to predict their strength. Up until now, we've been using values like the acid ionization constant, the Ka of an acid, to determine the strength of it. But there are also ways that we can examine the molecular structure to be able to predict which acid will be stronger than another. One category of acids we'll look at are binary acids. These have the general formula HX. Binary acids are going to have two different nonmetals, and hydrogen will always be one of the nonmetals. So whatever X is could change. We'll look at trends when acids are in the same family and trends when acids are in the same period. The second category we'll look at are called oxoacids. They have the general formula HOX. These are going to be acids that are formed from polyatomic ions. The identity of the nonmetal X will change for the various oxoacids. We'll look at oxoacids that contain the same number of oxygen atoms and they have a different nonmetal. And then we'll look at oxoacids that have the same central atom, the nonmetal, but they have a different number of oxygen atoms. The big thing to remember is that the strength of an acid depends upon how stable its conjugate base is. So if an acid has a very stable conjugate base, it's going to be a strong acid. The less stable its conjugate base is, the weaker that acid becomes. So we'll look at different ways that you can assess the stability of an acid's conjugate base that helps us predict its strength. Let's start with looking at binary acids that are in the same family or group of the periodic table. The size of the anion in the HX bond will determine the strength of the HX bond. So if we look at group 7A and compare some of the hydrohalic acids that have a different X or nonmetal, we can look at what each of the acids' conjugate base would be. So hydrofluoric acid will have the conjugate base of the fluoride anion. Hydrochloric acid will have a conjugate base chloride anion. Hydrobromic's conjugate base is the bromide anion. And hydroiodic acid's conjugate base is the iodide anion. Now notice in this case we are starting at the top of our family and we're working our way to the bottom. In each case, the size of the ion is getting larger as we go from top to bottom. So fluoride is a rather small anion and iodide is a rather large anion. As the size of the conjugate base gets larger, it increases in stability. So iodide is the most stable conjugate base of our hydrohalic acid group. Since iodide is the most stable conjugate base, that means that the acid HI will be the strongest acid. Since fluoride is the smallest, that's going to make it the least stable conjugate base. And that would make HF the weakest acid of the group. In fact, hydrofluoric acid is the only hydrohalic acid that's actually considered a weak acid, whereas hydrochloric, hydrobromic, and hydroiodic, those three hydrohalic acids are actually considered strong acids, and that has to do with their conjugate bases being large enough that those electrons can actually spread out and it makes that base more stable. So as you go from top to bottom within a family, and when you're looking at binary acids, the acid strength will increase. So that's the general trend. It doesn't matter if we're looking at group 7A, group 6A, as we go from top to bottom, the acids get stronger. Group 5A, they get stronger as we go from top to bottom, as long as we're comparing binary acids. When comparing binary acids that are in the same period of the periodic table, the size doesn't really change very much. So size is not going to determine the polarity of our HX bond. Instead, the major factor to consider is the electronegativity of the nonmetal. That will determine how polar the HX bond is and how easily it can break up into the hydrogen ion and X minus its anion. The easier that HX can break up into H plus and X minus, the stronger the acid will be. So if we compare HF and H2O, since they are in the same period, essentially we're comparing the HF bond to just one individual HO bond. We know that the electronegativity trend in general across the periodic table is that it increases as you go from bottom to top. And what we're interested in, since we're in the same period, is that it increases from left to right, with fluorine being the most electronegative element on the periodic table. So comparing fluorine to oxygen, fluorine is going to be more electronegative than oxygen. What that means is fluorine wants to pull electrons towards itself more. So if we compare an HF bond to an HO bond, the fluorine is going to develop a partial negative charge, and the hydrogen will develop a partial positive charge. Same thing with an HO bond, partial positive on the hydrogen, partial negative on the oxygen. But those electrons in the HF bond are being pulled even more so towards fluorine than they would be towards oxygen, since it's more electronegative. That makes the HF bond more polar. And comparing our HO bond, that would be less polar. So the more polar the bond, the easier it is to actually break up into H+ and its conjugate base. So that means that HF, hydrofluoric acid, would end up being a stronger acid than water would be. Water would end up being the weaker acid. So the general trend when you're dealing with a binary acid and you're in the same period is that as you go from left to right within a given period, your acid strength will increase. But the trend is due to the increasing electronegativity, which affects the polarity of the bond. If we just imagine we're looking at this small upper right corner portion of the periodic table, this summarizes how we can use our trends within given families or given periods to determine binary acid strength. So we could imagine as we work our way from left to right within this period here that our ability of these species to act as an acid is increasing. So hydrofluoric acid is a stronger acid than water. Water is a stronger acid than ammonia, and ammonia is a stronger acid than methane, which is CH4. The reverse trend could also be true. If that's our acid strength, there's an inverse relationship between acid strength and base strength. So going backwards now across that same period, we're increasing in the strength of those to act as a base. So that would make CH4 the strongest base. And hydrofluoric acid, HF, would be the weakest base. The same trend would work for the period below this first one. As we go from SiH4 to pH3 to H2S to HCl, we're increasing in acid strength from left to right across the period. The other thing is when you're working within a given family. As you go from top to bottom, the size of that anion, the size of that conjugate base is going to increase within a family. So the acid strength increases as you go down. HF is a weaker acid than HCl. Water is a weaker acid than H2S. Ammonia is a weaker acid than pH3. Methane is a weaker acid than SiH4. So every time as you continue to go down within a given family, the acid strength is going to increase due to the size of that conjugate base getting bigger. Whereas when you're working within a given family, it's the electronegativity that impacts the polarity of the bond and the acid strength. Identify the strongest acid in each pair. And we're going to want to use the periodic table to help us. So we have H2S versus H2Te. So if we identify where sulfur and tellurium are on the periodic table, we can see that they're both within group 6A. So they're in the same family. In this case, since tellurium is lower on the periodic table than sulfur, it's going to be a larger conjugate base that's formed. So that conjugate base will be more stable, and that would lead it to being the stronger acid. Next, we have HI or H2TE. So if we identify them, we have iodine right here and then tellurium right next to it. Now we're within the same period of the periodic table. So in this case, electronegativity is going to be our trend. Iodine is more electronegative than tellurium because it's to the right of it. So that bond is going to be more polar, and hydroiodic acid would be the stronger acid. HF versus HBr, we would find fluorine, and then we would find bromine, and we're once again in the same family now. So bromide anion is going to be more stable than fluoride anion because it's larger. So that would make hydrobromic acid the stronger acid. And then lastly, H3N or H2O. So we would want to compare nitrogen to oxygen. And those are in the same period. So oxygen is more electronegative, and that's going to be the stronger acid, water would be, compared to ammonia. Next, we're going to look at factors that affect the strength of oxoacids. Oxoacids are acids that are derived from polyatomic ions. They have the general formula H sub N X O sub M. X represents the non-metal portion of the oxoacid. N and M would represent the number of hydrogen atoms and the number of oxygen atoms in the formula. We're going to start with oxoacids that have the same number of oxygen atoms. The strength of the acid will depend upon the electronegativity of the nonmetal, or X. The electronegativity impacts the polarity of the HO bond. Electronegativity, as we've seen before, has the general trend of increasing from bottom to top within a family and from left to right across a period. So the least electronegative element is francium, and the most electronegative element is fluorine. In this case, even if we're in the same family, electronegativity is the general trend and not the size of the anion like we saw with binary acids, because with oxoacids, the hydrogen atom is bonded to oxygen in each case. So if we compare hypochlorous acid, HOCl, to hypobromous acid, HOBr, and hypoiodous acid, HOI, notice that in all of them, if we look at the Lewis structure, hydrogen is bonded to oxygen, which then has 2 lone pairs of electrons on it, which is then bonded to X, the nonmetal. So the electronegativity of that nonmetal impacts the polarity of our OH bond. And for the acid to dissociate, the hydrogen has to be lost from the oxygen. So the more electronegative that our nonmetal is, the more that it's going to be pulling those electrons away from oxygen. And then that's going to make oxygen want to pull those electrons away from hydrogen even more. So we're going to be needing to know that trend in electronegativity across the whole periodic table when we're dealing with oxoacids that have the same number of oxygen atoms. So if we look at our trend here, chlorine is the most electronegative within the halogen family, and iodine would be the least electronegative within that same family. And so the acid ionization constant for hypochlorous acid is greater than the acid ionization constant for hypoiodous acid. So that means that as the electronegativity is increasing, the strength of the acid is increasing. So the general rule of thumb is, if the oxoacid contains the exact same number of oxygen atoms, then the acid strength will increase as the electronegativity of the nonmetal increases. Next, we'll compare acid strength trends for oxoacids that have the same nonmetal but a different number of oxygen atoms around them. So if we compare the family of chlorine oxoacids, HClO, which is hypochlorous acid, HClO2 is chlorous acid, HClO3 is chloric acid, and HClO4 is perchloric acid. So notice all of these acids have the same nonmetal portion. They all have chlorine as their X. But what they have is a different number of oxygen atoms. starting with 1 oxygen for hypochlorous acid, 2 oxygens for chlorous acid, 3 oxygens for chloric acid, and 4 oxygens for perchloric acid. And in each case, notice that in an oxoacid, the hydrogen atom is bonded to an oxygen and not bonded to the nonmetal. So we can see that as we go from left to right, as the number of oxygen atoms increases, the strength of the acid increases. And this has to do with how stable the conjugate base is in each case. So you might remember when we learned about resonance structures last semester and how we could draw a varying number of resonance structures depending upon how we could move the location of electrons around. And if something has more resonance, it had a greater stability. So perchloric acid has more resonance in it than hypochlorous acid, and that's because of the greater number of oxygen atoms. So typically, if the oxoacid has the same nonmetal portion, the same X, and it has a different number of oxygen atoms, the acid that has the greater number of oxygen atoms will end up being the stronger acid. In each case, the oxidation number of the chlorine is also changing, so that's kind of another trend you could use. As the oxidation number of chlorine increases, the acid strength also increases. If we look at the resonance structures of our chlorine family oxoacids, we can see that hypochlorous acid has only 1 structure. Chlorous acid has 2 possible resonance structures. Chloric acid has 3 possible resonance structures. And perchloric acid has a total of 4 possible resonance structures that could be drawn. So this ends up being the strongest acid. ClO4 minus is the most stable conjugate base. The more resonance structures that we can draw, the greater the stability of that conjugate base. And if a conjugate base is more stable, that's going to lead to the acid being stronger. So in this family, hypochlorous acid would be the weakest acid. The quick way that we look at them to compare is just to simply look at how many oxygen atoms there are in that given oxoacid. Identify the strongest acid in each pair, HNO2 or HNO3. So HNO2 is nitrous acid, HNO3 is nitric acid. Nitric acid is one of the strong acids, whereas nitrous acid is a weak acid. For us, if we didn't know that, we could look at nitrous acid has 2 oxygen atoms, and nitric acid has 3 oxygen atoms. So the greater number of oxygen atoms will have more resonance structures for its conjugate base, and therefore it will be the stronger acid. H2SO3 versus H2SeO3. So here we have 2 oxoacids, and they both have the same number of oxygen atoms. So they both have 3 oxygen atoms. That's not going to be what we use to compare them. Instead, we're going to look at the electronegativity of the nonmetal. So electronegativity of sulfur versus the electronegativity of selenium. So we want to identify where those are in the periodic table. We have sulfur, and then we have selenium. And also our general trend for electronegativity increases from bottom to top and increases from left to right. So that would mean that sulfur has a greater electronegativity than selenium. So that's going to make the polarity of the oxygen-hydrogen bond in H2SO3 more polar than the hydrogen-oxygen bond in H2SeO3. So that's going to lead to H2SO3 as being the stronger acid. Next we have HClO or HClO4. In this case, we are going to be comparing the number of oxygen atoms since the nonmetal is the same. We have 1 oxygen atom or we have 4 oxygen atoms. The greater number of oxygen atoms will be the stronger acid. That'll be HClO4. Lastly, we have HBrO2 or HClO2. They both have 2 oxygen atoms, so that means we're comparing the nonmetal. We have bromine or we have chlorine. So if we look at the periodic table, we're going to identify we have chlorine here and bromine here. In terms of the trend of electronegativity, Chlorine will be more electronegative than bromine, and so that's going to end up being the stronger acid.